very fortunate to have Shlomo Shamai visiting us to give the talk today. And I first met Shlomo in 1992. It was the first talk I ever gave at Bell Labs. In fact, the first talk I ever gave outside of where I was doing my graduate study. And Shlomo, in typical Shlomo style, grilled me mercilessly on every single slide. But I managed to answer all his questions, and we became very good friends and collaborators for many years after that. So it was a good introduction to the very famous Shlomo Shamai, who once referred to me, if you remember, as that girl from Berkeley, which I guess shows you that, you know, I was famous enough that was a good enough introduction. Anyway, let me tell you a little bit about Shlomo's official bio. So he's got all his degrees from the Technion, 75, 81, and 86. He started out his career from 75 to 85 with the Communications Research Lab, and then joined the Department of Electrical Engineering at the Technion, where he's been ever since. And in fact, now he is a Technion Distinguished Professor. He was always a Distinguished Professor, but now he's officially a Technion Distinguished Professor. And he holds the William von Diller Professor of Telecommunications Chair. And his research interests, okay, so it says here, encompass a wide spectrum of topics in information theory and statistical communication. That is totally an understatement. He is a total encyclopedia of knowledge about everything in communications and information theory. And he's even cited to me papers from the Russian literature, just in case it wasn't enough to know all the English language literature. So if you ever want to know anything about anything, ask Shlomo, because he probably has read 10 papers on it. Okay, so on to the awards. He's an IEEE Fellow, member of the Israeli Academy of Sciences and Humanities. He won the 2011 Claudia Shannon Award. I'm not going to go through all of these, so I'll just mention some of the highlights. The 99 Vanderpool Gold Medal of the Union Radio Scientifique Internationale. He's won several paper awards, including the 2000 Donald G. Fink Prize Paper Award for a beautiful tutorial. Paper, he's won the 03 and 04 Joint IT and Comm Society Paper Awards and the 2007 Information Theory Society Paper Award. And there's a lot of other awards on here that I'm not going to go into all of them. He's also been associate editor for Shannon Theory twice, and he serves on once and twice on the Board of Governors, and he's on the executive editorial board. But I have one special announcement that's not on here because it's hot off the presses. Just this morning, in the middle of the night, in fact, he learned that he was inducted into the National Academy of Engineering as a foreign associate. So that's a wonderful, great thing. By the way, the boss was also inducted today, so congratulations to the boss. And I'll turn it over to the Encyclopedia of Information Theory, Shlomo.
Thank you, Andrea. I must say I'm a little embarrassed.
Good, that was the goal.
Too kind an introduction. Really too kind. So whatever I'll try to do today is to use the connection between information and estimation as a guideline in an effort to gain some insight into practical coding schemes with the emphasis on the interference channel. And while going along, I'll try to mention also open challenges that I hope you'll find interesting. So we will start by, first of course, this joint work with my former PhD student, Ronnie Gusti. So we will start by just reviewing some information estimation relations on which we'll base the talk and trying to gain some insight into specific codes, good and bad codes. We'll see why do we need to consider bad codes. And then examine information versus disturbance, where disturbance is measured through by the MMSE, minimum mean square estimation. Say maybe something, time permitting, about degrees of freedom. And then conclude with an outlook. As I said, throughout I'll mention specific research challenges that I think are interesting. So the information estimation relation for a very, the simplest model, the scalar model, y equals the square root of the SNR, which designates the signal to noise ratio, x, an input, n, standard Gaussian noise, Go, Verdu, and myself, Sergio sits here, very good friend. Derive this interesting connection with equality, the mutual information and the minimum mean square error of x when the estimation is based on y. Here we have different notation for the same thing. The best estimator, as we know with this performance measure, is the conditional mean. So here we have different notation just for the MMSE. And of course, if x is Gaussian, that's standard. If a classroom exercise, if x is Gaussian, then the optimal mean conditional mean is just a linear estimator. The MMSE is well known, the mutual information, the classical Shlomo formula, and the relation, of course, holds. For binary signals, again, a little more complicated classroom exercise. The MMSE can be also evaluated up to a single integral, the mutual information to say, and that relation holds, and we can see it on a graph. Here is the Gaussian case in red, the mutual information is a function of SNR, the MMSE, and the binary case. So let's look a little further for the vector channel that we'll need. Now, x is a vector input, h, the matrix, the channel matrix, SNR, again, the proportional coefficient that stands for signal to noise ratio. The vector y is the measurement, and the standard Gaussian vector n is the noise. The same thing holds. Again, derivative of the mutual information with respect to SNR is just because we consider real signals the half of MMSE of HX when it gets estimated based on Y through the conditional mean. Here is the MMSE, H is fixed unknown. So this is the MMSE, and it's just the trace of the covariance, error covariance matrix, the MMSE covariance matrix. So this holds for vector. Any vector with some conditions, say you even don't need the finite power thing, but say we have it. And that's for vectors. Again, just to exemplify, to demonstrate things, if x is Gaussian, the mutual information is the classical famous log det result. The MMSE is also classical result. Here is the covariance matrix. Again, under Gaussian, in the Gaussian regime, the optimal estimator is linear, and this is the MMSE that we need. The trace of this kind of a matrix and the relation holds. Just to demonstrate things. We'll need some notations, and we'll look at vectors afterwards to be used as codes. And the vectors of length n, gamma here will stand for the signal to noise ratio, which may change. And when we have the index n, finite n, the mutual information is normalized per symbol. Whenever this index is not there, just means the limit as n goes to infinity. The same goes for the MMSE, where the upper script C stands for code that we'll use. So that's just the convenient notations to be used. Whatever we'll need afterwards is a property that we call a single crossing point property. Again, appears in another word like go, vu, verdua, myself. And it has to do with the following function. What is this function? The difference between the MMSE of a standard Gaussian input, we saw it's 1 over 1 plus SNR, here it is, minus the actual MMSE for that any x that is there. Here it's presented for the scalar chart. Of course, if x has a variance of 1, this is never negative because the MMSE of a Gaussian is an upper bound. If x has a variance larger than 1, it starts as negative because of SNR 0. This is 1, and this is the variance, which is larger than 1, so it's negative. The idea is that this function can be shown when it starts at a negative number, it keeps increasing, reaches 0, and that's it. It stays above 0. 1, 0, close. Then for when SNR goes infinity, of course, it goes to 0 because both ends. So this goes to 0 and the other one goes to 0. So there's only 1 0 crossing of this difference, of this function. And that has been used in that specific paper, for example, as an alternative proof for the scalar Gaussian broadcast channel, the capacity region, which is well known, without relying on the entropy power inequality, as originally was done. Just via this property alone. Here we will need it for something else. This was the single crossing property for just a scalar chart. For a vector problem, things are a little more complicated, and there are different results of this sort. All appear now in this paper by Bustin, Payaro, Palomar, and myself, appear just in the February issue of the IT transaction. And here we need only the very simple result. Most of that has to do with single crossing of eigenvalues of this error covariance matrix. Here it's very simple. We have just inputs which are IID and which are not IID. The H matrix is I, the identity matrix, and the X are of variance sigma squared. So this is the very simple thing, and it behaves, though it's a vector, the very same thing as the scalar case. Starts negative, if it starts negative, if the variance of the X is large enough, increases, crosses 0, and stays above 0, and goes to 0, like we saw for the scalar. Just works also for a simple version, vector version with a simple H, which is equals to the identity matrix. Okay, after having this reviewed, let's look at codes. Now, our input is just a code word of a code word of length 10. That's all. All those things work. So, if we have such a code, if we interpret this as a code, the input on a Gaussian channel, of course, what can we say if we know that the code is good? What do I mean the code is good? A code on that Gaussian channel achieves the capacity of that channel for a given SNR. It achieves half real signal, half log 1 plus SNR. How the mutual information of this code behaves, and how does the MMSE of this code behave? Of course, if it achieves capacity, by definition, it has to be infinitely long. Then it has been shown by those three that a good code that achieves capacity, but the mutual information must behave exactly like that, meaning it increases with SNR as Havelock 1 plus gamma until we reach the SNR for which the code was designed. Then it achieves capacity and stays there, of course, as decrease. God gets the code. And the MMSC behaves like that. It decreases like the system was uncoded. So the structure of the code is useless. From an MMSC perspective, until you reach that SNR where you can decode the code. And then it drops to 0. You decode the code reliably, that's it, no MMSC. So it's just depicted here. So the mutual information raises, increases, and then you reach capacity, it stops, and the MMC behaves here and falls in a phase transition to 0. This is a good code over a Gaussian chart. Any good code will behave structure, not structure, any. So just as a backtrack, maybe a comment, this kind of an observation is good, not also, good codes, optimal decoders. It's good also when you try to gain some insight into the performance of actual belief propagation-based decoders, not optical, of course, and codes of given structure like LDPC tool. And here what is plotted is the exit chart in extrinsic information chart. Here is the input information, this is the extrinsic information at the output. For a good code that achieves capacity, it behaves like that, again, as a threshold, meaning whatever the information at the input, at the output, the extrinsic information is just 0. Until you get to a threshold, you get the full intrinsic information, and it connects, of course, the classical things which are known as the area theory by Ashimkin, Kramer, and Ten-Brink, or general exit. Andrea Montanari, who is sick, unfortunately, and Richardson, Barker, Mason. It's very, very closely connected to those results. And it shows what? That good codes are not good at all as component codes of say, a turbo coding structure. Why? Because in a turbo coding structure, you expect information to build up, not to behave like that, which is useless. To build up. Slowly, on an exit chart. And actually, even if in the original papers, it was empirically noted by Beru and Glovio that when they put as component codes, even strong convolutional codes, it didn't work. You had to put quite simple codes as component codes. Now we see why. If you put too strong codes, useless. Belief propagation, forgettable. So that's just to show we will not bother about complexity in the stock, but to show that things might be even useful under complexity course. That was very fine, but transmatic. Good code is very nice, but we are not alone in the world. Once you X transmits to Y, that's very nice. It, in a way, can interfere with another node Z that is not exactly interested in that information that X has to transmit, and somehow this interference has to be controlled this way or the other, or another. Standard things are resource allocation and think of this sort. So whatever we have seen, that good codes from here to here are very nice, but they inflict the maximum possible interference if we measure interference as MMSC. And we assume that this channel from X to Z is worse than X to Y. Otherwise, the problem is much simpler in this idealistic setting, because if Y can decode Z, of course, can also. Unless the channel to here is not that good as the channel here. So, okay, so if you inflate the interference, you somehow you are forced maybe to avoid good codes. They are very good for the person you are communicating to, but not that good for to whom you interfere with. So, if we limit interference, how much do we have to back off from a good code in a way? So this kind of codes, of course, are called bad codes. Bad, the meaning of bad is, of course, not really bad. So bad codes trade, if we measure interference as MMSE versus in the lower SNR, if we speak about Gaussian channel, versus the code rate for the better user that wants to decode this code. And this kind of specific structures of LVPC code has been recently investigated by Benatan or Calderberg or myself. And this of course kind of steps back from standard point-to-point codes that have been considered by Bacelli, Abbas here, David Tse, and in a way still use one code, but somehow you want to do partial interference cancellation. And that could be done. And not only, the code can be designed this way. And here, for example, here is the graph which corresponds to good code. As we said, MMSE decreases like it was encoded and breaks down to 0, phase transition. And here are specific LVPC codes that are designed through those in that paper, where the graphs are bounds, are actual bounds using different techniques. One technique uses the Weichmann-Sasson information theoretic observation, the other is based on belief propagation. But we see, okay, you are, for the beta region, you are worse, you lose weight, but MMSE, you win, so you interfere less. Okay. Having said that, in a way we are ready to set, to formalize a very simple problem, optimization problem. Say we have two SNRs, SNR1 smaller than SNR2. The MMSE at S, at the smaller SNR, the channel that we interfere with, is an interference measure. We want it to be not that large. Okay, so if we constrain that, what is the maximum mutual information that we have at the larger SNR, which is our legitimate user? So the problem is maximize ISNR2 under the constraint such that the MMSE at SNR1 is controlled better. The controlling factor is not larger than that. Of course, if we choose beta equals 1, no big deal. Beta equals 1, we have the full ISNR, because that's what we saw with the good codes. If beta is smaller than 1, probably we'll have to do this here. So this clearly, and of course idealistic, some kind of an idealistic or a naive problem, but still, I think a nice problem that will give insights from. Before going through the solution of this problem, let's look at classical superposition codes and how do they behave in terms of I and MMSE. So classical superposition codes that are, for example, used on the, here we have just a Gaussian degraded channels. Whatever we have in classical superposition code, like the Gaussian broadcast channel, it can be shown here in this work. Merhav Go and myself using actual statistical physical methods, not replica methods, not replica, the exact results, to show that the mutual information behaves like that, meaning increases as before, like half log 1 plus gamma until some threshold SNR, then the slope changes, becomes lower until the other SNR, the higher SNR, SNR2, and then stops, stays constant. And the associated MMC behaves like that. Let's see it on the graph. Okay, that was a good code, the blue curve and the MMC. So here we have a superposition code. It behaves like that. Here we have the first phase transition. Here the second one, and the mutual information, as we see. Here changes slope at SNR1 and doesn't reach. This is the penalty that you pay with superposition coding. So the theorem for this optimization problem also appeared in the February issue of the IT transaction, is that superposition coding solves this problem. This is the whatever is associated with superposition coding actually is the solution from this problem. For this problem, how do we show it? So that says that the maximum of ISNR2 is equals to that here, and this is a function of this beta that controls the interference. Attainability, achievability, we know superposition coding just we show the achievement. How do we show that there's nothing better? So let me just go through a proof sketch quite rapidly. So achievability, no problem. We just seen that it's okay. So whatever we need is an upper bound on the rate. Or alternatively, we say that the rate achieved at the good SNR, the SNR2, is half log 1 plus alpha SNR2, where alpha is smaller or equal than 1. Let's see what happens with the MMSC. Of course, if gamma, if this SNR is larger than alpha SNR2, then there's no MMSC. Beta is equals to 0. Why? And beta at the point gamma. Why? If that code was detected at SNR2 with this rate, for higher SNR, of course, it gets detected perfectly, and that's it. No MMSC. So this is the interesting region. Gamma is smaller than this, alpha SNR. Okay. So the mutual information at SNR2 minus the mutual information at the point SNR equals gamma is larger than the difference of that. Why? I gamma is always smaller than half log 1 plus gamma, which is the rate of the code, and SNR2, the good receiver, minus the. Okay, but we know that this difference of mutual information is exactly the integral of the MMSC from gamma to SNR2. That's the difference. And now we see that it's larger than this. Fine. If it's larger than this, let's find D, always can be found, where this difference equals to that. And D, of course, will depend on gamma. So we have that the integral of the MMSC between those SNRs, gamma to SNR2, is larger than this, which equals to this. And what is that? Is the MMSC of a Gaussian with variance D. It's exactly that. What does it mean? It means that if we have the actual MMSE between that equals to the Gaussian MMSE of variance D, that means that there is a single crossing point, because it's an inequality, not an equality, that happens somewhere between gamma and the infinity. Remember, the Gaussian must cross once. Okay, if that happens, then the MMSE at point gamma is still before the crossing point. Meaning what? That the MMSE of the actual vector x is larger than the Gaussian. So we have this. That concludes the whole proof. Just connect alpha to that beta to the relations that we found. That's it. And it's really interesting that superposition coding solves this problem. Remember, n goes to infinity, which will be a challenge if we depart from it. Actually, one can show more. One can claim more. And that theorem says, look, if we have a reliable a set of reliable codes with this rate that comply with the MMSE constraint, we see that there is something like that, and this is the MMSE constraint, then the superposition coding not only actually achieves this, meaning complies with the constraint and achieves this rate, but it provides the minimum MMSE over all SNRs. Which is nice. Still, we haven't got any interpretation on insight from that. An extension of the whole thing is to K points. After all, we may interfere with many receiving points, not only one, at different SNRs. So now you want to constrain the interference at many points, here at K points, and still maximize the mutual information to the best SNR, the legitimate receiver, under all these constraints that should be satisfied. And also this can be solved exactly analytically in closed form. And no wonder that we did superposition coding with many layers, not 2 layers, does satisfy that. The proofs are rather similar, so I won't bother to sketch it. And of course, here some of the constraints may be not effective. Meaning if you satisfy one constraint, the other is satisfied by itself. So here are the conditions. But the idea is to keep this in mind, that superposition coding really solves this kind of a problem completely. And here just showed the figure for trio. Meaning we have 2 MMSE constraints, not redundant. Here is 1, 3 SNRs. Here we interfere the SNR of the good receiver is 2.5 from another receiver that we interfere is 1.8, the third receiver 0.8, and we demand the MMSEs to be, which are interference measure, to be not larger than that or than that. So we have to pay a penalty in a rate like this, where again the blue curve is an optimal, a good code. This is the maximum rate at the highest SNR, and this is the associated MMSE, which doesn't satisfy the interference. Whoever does are 3-layer coding, superposition coding. They're just a figure base of that theory. Okay, so let's step back and see maybe some kind of an, how shall I say, engineering insight. Using MMSE as a disturbance measure, and which led actually to the result that of the optimality of the superposition coding provides an intuitive engineering support for the for the fact that Han-Kobayashi region is something not that bad. Maybe not optimal. Why not optimal? Not only why not optimal then on the Gaussian let us not forget the optimization problem was naive. The interferer, where we interfere, we do not assume that there is another signal, which is the signal that it wants to decode. So optimal or not optimal, we don't know, but at least gives a good engineering feeling that's something not that bad. Of course, for the two-user Gauss interference channel, we know it's not that bad. It's the Atkins-1 result says that at most within 1 bit of the unknown capacity region of the cell. Not that bad, but the truly engineering feeling one gets through this. And another quite recent result by Abbas, Bandivir, and Kim says that, look, even though the kind of superposition coding with the code remove interference, like simple things, practical things, even with random code, even if we did maximal likelihood, optimal decoding, meaning we know the code book of we are not interested in the other code book. We do optimal decoding, we get nothing. That's a very recent result. And that's quite interesting. And, okay, so far, two-user interference channel maybe that's fine. What about K users, like we extended this optimization problem to K users and still we had that superposition coding is good? Can it be at all a good approach? To use superposition coding, maybe it misleads us this insight. If you use superposition coding on the K-user interference channel, in a way it leads to, at least from degree of freedom of 1. And we know that this is not exactly the case on the K-user interference channel. We know that this immaterial how much important is this degree of freedom. We know that sometimes it's K over 2. What's going on here? So is this insight misleading? Actually, not exactly. It's not that the IMMSE relation is misleading, not at all. But once you consider true interference channel that has been done by Alice Wort again, by both Sergio and myself, using maybe either Reni information dimension on something which is much more engineering, as an engineering interpretation, I gave the work of Wolf, Verdu, MMSE dimension, which says how the MMSE decays with SNR, which happens to be the same as the Reni mathematical dimension. Let's not go through the definition, for a discrete or continuous or a mixture random variables. If one uses this, why does it interest us at all? Because of this. Again, this gives the true DOF degrees of freedom, whether important or not, that I won't argue, relation. So, without the interest of time, without going too much into details, this MMSE dimension may lead to the right conclusions, meaning that if you have irrational if you have, for example, off-diagonal, the interference Gaussian, interference channel, if the off-diagonal elements are rational and diagonal elements are irrational, then you have this k over 2. That's why I wanted also to skip it, because I don't want to argue how much important is having a rational or irrational on the difference between that from a practical point of view. But that's just to say that MMSE and IMMSE doesn't necessarily lead you to a more kind of engineering conclusion. Could give the very, at least mimic or reproduce known results about degrees of freedom. Also for a k-user interference chance. For a 2-user interference chance, well known, degrees of freedom. 1. So again, let's put one challenge explicitly in, and that's again, whatever I did actually is the simple problem. Took n to infinity. Why not stick n here? Look at really at vectors of length n and repeat the problem as is. Maximum the mutual information for something, for a vector of length n under the MMSE constant, satisfy the MMSE constant. What happens then? N goes to infinity, fine. Superposition solves it. Finite n, I have no idea. Not only I have no idea, say n equals 1. Nothing related to coding, really simple problem. My conjecture that the optimization is a discrete input. So we allow for continuous inputs like that. So no, optimization of this is discrete. That's a conjecture.
So why do you have a CN in the MMSE?
Because those are denotation, but n is fixed, not C, and C stands for a code of length n.
Right, but aren't you optimizing over X, which is now random? It's not an entry from a code book.
No. You optimize over any X of length n with a fixed power. Any. It will be.
I guess the question before you were saying it's going to be capacity achieving. And now there's no.
Now
there's still a code here.
There is only a vector X that you want to achieve mutual information with MMC. It's not clear that IID is the.
Okay, so no, but then isn't the MMSE, the MMSE has to be this X based on channel output, scenario 1. So the CN there seems.
No, CN just says that it's
It's
an
a
input,
vector.
a vector of length. That's all. Not infinity, that's all. Vector of length, whatever.
But then relating back to Sergio's question, why is this interesting from an operational viewpoint? To achieve this, you're going to need very large block lengths.
Maybe we'll come up with like the results that Sergio came up for block length. The second, the approximation. How do you approach the infinity and gain much insight into that? How with increasing n, it goes to superposition. Maybe not in a very simple way.
Or maybe it looks like a completely different code.
Might be. I wouldn't even want to say
but
what.
then conceivably the target function is not mutual information.
No, it's not that you use this code that you will get, you'll get the right mutual information, hoping that the probability error won't be too bad if n is large enough, but not infinite. You really want some kind of, like the work that Sergio did with Yuri, you want something, another thing of how it behaves. But the problem is that even for n equals 1, which is the problem, it's almost a trivial problem. It's not as trivial, but it's not. So, another disturbance measure which was again suggested by Abbas and Bandimir, is just measure also disturbance by mutual information, not MSC. So whatever you want to do is again maximum mutual information to the good user and the higher SLR user, and limit the mutual information to the user that you interfere. Right? Another disturbance measure. You don't, in a way, assuming if that guy doesn't have too much mutual information, the interference is not that bad. So it's another disturbance measure. Also, MMC is kind of an arbitrary disturbance measure. Okay, so this is the problem that Valdivia and Gamal have solved. Again, maximize, same problem, maximize with another disturbance measure, maximize the mutual information at SNR2, assuming that the mutual information, the lower SNR, satisfies this constraint, meaning it cannot be larger than half log 1 plus SNR1, but you choose alpha that you're satisfied with. What is the maximum of this? And they have shown that the maximum is that, with the same alpha star. And again, the proof was based on entropy power inequality, and it is achieved by any IID Gaussian. This solution is true for any, achieved by any IID Gaussian input with variance, not 1, but alpha star.
But, in our original, we started with discrete memories and we got this proposition.
Yeah, not only that. Also even in Gaussian, but in the MIMO case still.
Yes,
The MIMO.
exactly. Yeah, that kind of degenerated.
Yeah,
The MIMO is fine.
MIMO, even the Gaussian.
Yeah.
So, this is the result with that disturbance measure. Again, the original proof was based on entropy power inequality. Let's see the proof is serialized with IMMC of this thing. Okay. So at SNR1, say we want, this is our constraint. Alpha star defines the constraint of the SNR1. Here it is. So, what do we have? This is achieved, as we know, for Gaussian with variance alpha star. If it is achieved but Gaussian with variance alpha star, what do we know? We know that that Gaussian actually, if the integral of MMSC between 0 and SNR1 is equal from the right of the exact MMSC with the Gaussian, it says that the crossing point was somewhere before SNR1. The integrals are equal, so the Gaussian at SNR1 was already stronger. So what is the mutual information at SNR2? Just the mutual information at SNR1 plus the integral of the MMSC from SNR1 and SNR2. But the crossing point said that from even before SNR1, the Gaussian is already bigger. So, okay, so it's bigger. You put here a Gaussian and you get this bounded, that's it. This is the proof. Also the extension of under the mutual information disturbance measure to K constraint is very simple, and actually the constraint that covers is everything is the worst case constraint. You just choose what constraint is the variance of the input, the smallest that will satisfy it. Right is so, as we said, Abbas here said, indeed, if you look just at this example, then MMSC kind of provides more engineering insight. Because even for this simple case, MMSC led to superposition coding. Abbas mentioned that also the mutual information constraint, either for general channels or even for Gaussian channels. But in the MIMO, not Scala, the MIMO setting leads indeed to a superposition solution, even with the mutual information disturbance constraint. And here is the, hasn't been published yet, no?
No,
So here is the,
it takes forever.
yeah, here is the archive.
It's a
Here's
symptotic,
the-
actually.
You're going to
Not
fix
finite.
that.
It's not finite block length.
So V2 is the version that includes the MIMO result. So, and of course, immediately it actually leads to a challenge also from an MMSC constraint for the MIMO case, which is another problem. But again, DOF has been considered very recently by Stotz and Bolsky. There are interesting things there, especially, on scalar cases, singular random variables are very strange. On MIMO cases, singular random variables could be very simple, just a subspace of the original space, like 0 force. Very simple, very generic. And another challenge is again, like other work of Abbas and Vladimir Zakharyan, we want single code, no superposition. Who needs superposition? Or either that work with Benatan and Calderberg. Single code. You design single code. Optimize a single code with the constraint, with the with the interference of the disturbance constraint. That single code, no superposition. Okay, so you won't get the optimal, but still, how do you impose the single code on such an optimization problem? If you phrase an optimization problem, how do you impose the fact that you want a single code solution? And this, I think, is quite not that difficult. You allow only one phase transition. And actually, those phase transitions, which I didn't mention, I just used the terminology, are truly phase transitions. That appears in this work by Merhav, Guru, and Vital, which based on physical techniques that indeed it is a phase transition in all its physical meaning. Not just jump like we see. So whatever I try to do here is indeed discuss kind of how shall I say, simple or even naive optimization problems, but still I hope that do carry insights about coding in interference channels, and the basic underlying tool was indeed this information estimation relation. I'd like to thank you.
Are there any questions?
So are there any proofs that use the entropy power inequality that you have not been able to redo using algorithms? Tried and failed.
I would have liked to answer no, but the unfortunate answer is yes. That's the capacity of the minor broadcast channel. I am in the sea quite hard.
So all scalar problems.
Scalar problem. And it's not because maybe the tool is, it's maybe the way we try to do that. And that's my feeling. There's not right, not through the right, not through the right way. Trying to use more what worked in the Scala, this kind of.
What about in source coding problems? multiple description, Gaussian multiple description, stuff like that. How do you be the
Actually,
useful
yeah, actually, IMMSC, kind of, it's easy to address this kind of problems via duality aspects, like source coding with site information you interpret as in a way.
Yeah, but the multiple description
Multiple description, so whatever you try to use MMSC is more or less you fall back to the Gaussian setting. And that's too limited. The question is, so maybe IMSC is very nice, even if you couldn't solve many problems like the Gaussian minor project, still it's limited to Gaussian charm. The idea is that's not the case. But then you have to use stronger tools like the Verdun work of 2010, which gives a relation of divergence in general. So it could be a mutual information of a genocide as a difference between match and mismatch in the sea. Or, alternatively, also in the Gore Shamai Verdun paper, the original one, 2005, the mutual information on a very general chart was given as a difference between two MMSC, with more information or less information. So maybe on a two MMSC of a Gaussian chart, maybe that is useful. I suppose.
So just to distill one polite problem, you're saying that for maximizing mutual information across a Gaussian channel, under a constraint that the conditional variance of the input in the output is bounded by something, you conjecture this is achieved by a discrete input distribution.
I was brave enough to conjecture that for n equals 1.
Yeah, no, this is for any one.
Where I have some evidence.
Okay, but you have evidence that, say, the Gaussian input here is sum.
Yeah, that's easy to do. That's for sure. But if it's discrete, just too close with if you examine the relations, you're in a way quite close to the original Smith problem. But not exactly that, well acquainted with Smith's results, so it was really close.
I have a question on the K-layer superposition coding. Do we get any insights on which user is being decoded first and which user is being decoded next, and so on?
Yeah, here it's very simple because it's kind of a degraded Gaussian chart. That's the only thing I presented. Then what goes on the broadcast degraded Gaussian chart is good here. So the better chart decodes both users. And indeed, maybe the question is that maybe on other settings it'd be good, like general broadcast chart. Everyone might decode its own message, and nobody decodes both. And that might be advantageous. That's actually another work that I did cite, another work that was on archive 2 days ago, by Abbas Pandemia, examines exactly this problem. Covers superposition coding, which doesn't demand both the coding, top covers, latent coding. standard superposition coding that is used on a Gaussian degree broadcast channel that does, and they are not the same in general.
So for this non-Gaussian conjecture, discrete conjecture, for the one-dimensional case, maybe it would be easier to consider a related problem, which instead of having a constraint on the element C, which is really a proxy for not making it too Gaussian, right? So maybe you could have a lower bound on the non-Gaussianness, on the relative entropy with respect to the Gaussian.
Maybe.
That may be solvable.
Maybe, no, I even don't say that the original problem is not solvable, even if it has in more time. It's really not that hot, the n equals 1 after all.
So,
I think it's solvable. Still, the fact that you know that this is not that doesn't give you work to do to find the exact solution. You know, in the split case.
So, can I make a comment on when you mentioned why is it that it's because the other ignoring the other transmitter, right? Why is it that? So the thing is, with the mutual information definition that we use, you get superposition is optimal for the deterministic channel. And so everything fits perfect, even though we didn't consider the other guy.
Yeah, that I know.
You see, so that fit everything, right? But once you start putting noise and stuff, then all that's off.
It's very true.
So yeah, it kind of fell apart, right? So it's a little complicated. I mean, it's not clear.
Yes, whatever I try to say, that maybe it comes even not mathematically.
Yeah.
Engineering is it's not a bad idea to work with, as we well know from exact result, 1 bit to
Right.
maximum 1 bit of close.